Anyone can access deleted and private repository data on GitHub. Now, this is a write-up, a little bit of an article that was put out by Truffle Security way back in July of this year, and I would like to walk through it, I'd like to showcase it, maybe do a couple demos here. It says you can access data from deleted forks, deleted repositories, and even private repositories on GitHub. This is known by GitHub, it's known information, and it's intentionally designed that way. But it could very well be considered an attack vector. And honestly, they thought this is worth some whole new term. Coining some phrase here, cross-fork object reference, or CFOR. Very similar to an insecure direct object reference or an IDOR, CFOR users supply the commit hashes to directly access commit data that otherwise would not have been visible to them. Now, that does have a certain dependency. You need to know the hash. You need to know the unique identifier for each commit. And you might think that is a protection mechanism, but sort of kind of. We might be able to get in the middle of that. So here's an example. Accessing deleted fork data. Couple different steps here. Let's say you found a repository out on GitHub that you liked, you thought was cool. So you created your own copy, your own clone, or at least a new fork of that public repository. And then you add to it. You tinker, you add some new features, you do whatever you do, but then maybe you just put it away, you're done with it. It wasn't really all that worthwhile, so you delete the fork. But if that happened to have any sensitive information, maybe code, maybe API keys, maybe passwords, credentials that probably shouldn't have been in the repository to begin with, but maybe for whatever reason it is, or anything that you just added to the repository that you no longer want part of it because you deleted the repository, it's still accessible, but in kind of an interesting way. And let's see it here. Is the code you committed to your fork still accessible? It shouldn't be, right? You just deleted it. Turns out it is. And it's not something that you longer can really work with. But let's see it in action. So for a showcase, I'm going to be working with a GitHub org, GitHub organization, just JHLLC, and my own GitHub user, John Hammond. So I will create a public repository. We can mark this as public in my org, JHLLC, and we'll call it just initial org public. How about that? Should be just fine, doesn't need a description. We can go ahead, add a README file and create it. Click that button and it'll build up a repo. Now in this scenario, say that I, just regular John Hammond, that user scrolling around across the internet, I see this as a cool project, something that I want to fork, I can go ahead and do that. I'll create a new fork as just my regular user John Hammond, and we'll call this forked org public. It'll go ahead, fork the repository, and then we will add our own commits, our own changes, modifications that we might like. Let me go ahead and simply just edit the README. We can just add some new text here. My own fork. We can go ahead and commit those changes. Goodbye me. Now, if I go take a look at the commit here, we'll be able to see the unique SHA-1 hash and identifier for this commit. You can see it displayed up here, at least as a short rendition. We have a couple starting characters of what is a SHA-1 hash, but if I were to copy that whole syntax, I can just paste it down below so you can see that is the entire ID value. But GitHub really only needs to work with either the first 4 characters or 5 or 6. 4 is the shortest that it can be for a short SHA-1 hash. So let me put these side by side and you can see this all together. On the left-hand side, we have the JHLLC initial repository. On the right-hand side, we have the John Hammond forked repository. So this one is the one that has the one commit that is ahead. We've made those changes on our own fork. And I could go access that if I were to add into my URL bar here, /commit, and I'll go ahead and enter / for that SHA-1 identifier. Once I hit enter here, it tells me about the changes that I made, that actual modification. Bringing this over to the left-hand side for the initial repository, it's not going to be included there. At least it shouldn't be, but it is, right? Because it's a commit that's from a fork of that repository, but not specifically that repository. At the very least, it's still accessible and visible though. Now say I were to go back over to the right-hand side for my fork and I were to go delete this. Let's get back into the settings. Let's go ahead and delete this repository. I can go ahead and copy and paste this to make sure, yep, I'm good deleting it. Let me go ahead and delete. And once that's done, I will try to go to the exact same URL that I had previously for the forked repository, but it no longer exists, right? Forked org public commit that identifier, it's a 404. But that fork has now been moved in the GitHub fork network to the upstream repository, the original initial org repo. So I can refresh this on the left-hand side, and it's still there, despite it being deleted from my perspective. Oh, and one of the folks from Truffle Security did record a video on all this, and I'll sprinkle that in here and there. This is what Dylan had to say.
Things that you commit to a GitHub repository don't get deleted, ever. Even when the branch that they're committed to gets either deleted or overwritten with a tool like BFG. When that happens, those commits enter what's called a dangling state. Those commits can't be seen in the history and don't get downloaded when you do a clone.
But I know what you're saying here. You still need the commit ID. You need that SHA-1 hash. And they note this in the article. Hey, you might think that you're protected by needing to know that commit hash. And you're kind of right, sorta. Don't forget about that short SHA-1. That's a much smaller key space to potentially brute force. And given enough time, that's totally doable. And as it turns out, you might actually be able to find some pretty juicy data from this. Truffle Security had apparently tried and tested it here. They ask, how often can you actually find data from deleted forks? Apparently, pretty often. They surveyed a few, literally just 3, commonly forked public repositories from some large AI company and easily found 40 different valid API keys from deleted forks. The user pattern seemed to be just this. Fork the repository, hardcode their API, because they're using it for their own use, hey, whatever tooling that they might just grab, they do whatever they want, and then once they're done with it, they just delete the fork. But that's still going to be accessible now that it's been bubbled up and pulled into the upstream branch, or repository, sorry, I want to be accurate with the terms here, and that is still accessible, even publicly, if you can track down or at least determine the short SHA-1 hash identifier for each commit. So in just a second, we'll actually see how we can brute force some of those SHA-1 hash commit ID values. And we'll see what more could be done with this, like accessing deleted repository data under certain conditions. But before we keep going, let me tell you a little bit about the sponsor of today's video. Do you ever feel like you need to complete a million tasks at once while the security of your application is resting on your shoulders? That's where our sponsor, Snyk, comes in. Snyk is your inside helper in the world of application security. With Snyk, you can find and fix vulnerabilities in your code in real time and get the security intelligence and remediation advice that you need without disrupting the development workflow. So get peace of mind with Snyk and sign up for a free account today using my link below, jh.live/Snyk. Huge thanks to Snyk for sponsoring this video. Alright, now I'm inside of my Kali Linux virtual machine and we'll start to write some scrappy code just as a proof of concept. I want to see, hey, how realistic is it that we could actually track down one of those GitHub commits? So let me open up a terminal with Control-Alt-T on my keyboard. I'll hit F11 to full screen and I'll make a directory for us to work in. We can just call this like commits playground. And with that, I'll change directory in there and create a new simple playground.python script, .py. Now this is just going to be super scrappy, pretty bad, proof of concept, crappy code. Let's get a shebang line going though, and let's know the amount of characters that could make up a SHA-1 hash, right? It is just a hexadecimal hash, so we're expecting A, B, C, D, E, F, all those letters to make it hex, and then the numbers 0 through 9, as you would expect in the decimal representation. But hexadecimal being 16 characters, we've added our A through F. Now, if we wanted to actually make all of the potential possibilities that could make up a hash without actually hashing data, but just trying to enumerate all the possibilities, well, we would like all the possible combinations or permutations of the characters here. Now, normally you can do that with itertools, one of the sweet libraries that is part of Python, and you can use combinations with replacement, combinations on its own, or permutations, and even another called product, usually for a Cartesian product, but we could actually specify that for any that we might like, because I have not yet seen the exact, like, all the possible characters to the correct power with combinations with replacement or permutations, but maybe I got it wrong, so please let me know in the comments below. Let's define just a simple function like all possibilities given any of the characters in the character set. And Itertools actually returns a generator, so we will need to yield. And in Python 3, you can use yield from to actually end up calling a function in place there. So let's use itertools.product, and we'll take anything from the characters, but actually I want to repeat them. I want to repeat a given character to the certain length that we're looking for. In this case, a length of 4 for the shortest possible SHA-1 hash. So just an example, let's actually include a length argument as well. And we could say, look, get me anything from the characters times the length that we provide. And product needs to have a whole list on its own. So what you could do here is actually use that star operator to let that be expanded in place, and Python should handle it a-okay. With all that done, we could start to loop for P, any sort of possibility in all of the possibilities, given the characters that we provide with a minimum length of 4, and we could go ahead and print these out. Printing out P all on its own would just give us, if I actually run this code, all the values as a little tuple here. You can see the parentheses surrounding it, so we could join that together with .join. Printing this all out, you can see all the possible beginnings of what we'll consider the start of a SHA-1 and short hash. So we could say SHA-1, or just like short hash, whatever we want to call that variable, and then we could do a simple request. We'll go ask the internet. We'll just literally go to that URL over GitHub and then say, hey, can you tell me if you have a response here? Is that a valid commit? So we can take literally the URL of the commit that we looked at previously for the public repository, the top level upstream source here, right? And that will end up including our short hash. I'll make this a format string with the F prefix, so that will work just fine for us. And then we can go ahead and just ask the internet, import requests. Let's do a request.get on that URL. We can say that can be stored and captured as a variable or object R. So I can test if r.status code is not equal to 404, like it's not found. Like in the case of our deleted fork, right? That is what we don't want. We're looking for, oh, do we get a hit? Can we find it with a 200 response? Status A-OK. But it might be good to get anything else in case there's anything we're not expecting. So let's just do not equal to 404. If that is the case, let's print out the short hash on its own, even the status code that we observed and the URL that it reached. And I know this is pretty crude, right? It's a dumb little brute force, but look, if you want to see it work here, we could try and print out maybe trying, given one specific short hash. And then we could see over and over and over again until it finds one that it likes, it gets a hit, and maybe we just break out of the function. Getting back over to my terminal just to even try this, it will go through and brute force over and over and over again, but you'll see this is pretty slow, and eventually GitHub's probably going to get angry at us and whine and say, hey, you're beating up our services, you're going to be rate limited, yada, yada, yada. So I'm going to stop this, and we can think on, hey, just for the proof of concept's sake, how can we make this smarter or stronger and faster for us? Before we do, though, I do want to showcase some of the other sweet stuff that could come from this attack surface, like finding the deleted repositories, or at least the data and commits that would have been present in that repository. That is this scenario. Say there is a public repository on GitHub, just like our initial org public that I created for JHLLC. Say a user, like my John Hammond, forks the repository, and then the original initial repository adds new data. They commit new things after it has been forked by someone else, and that other user never ends up syncing their fork with your new changes and updates. But let's say that you, the initial org owner, delete the entire repository. So all of your code from the initial original repository should be gone, right? That's been deleted from GitHub. This does have a very defined start, though. It is once another user forks the repository. Then the commits that followed after that to the original repository will be made available on their fork, not your repository once you delete it. Kind of weird, kind of wild, but that's what they showcase here. Is the code you commit after they fork your repository still accessible? Yes. Even though you deleted what you thought was your repo, GitHub stores repositories and forks in a repository network, with the original upstream repository acting as the root node. When a public upstream repository that has been forked is then deleted, GitHub will reassign the root node role to one of the downstream forks. One kind of threw me off for that key word there. They did continue, though. All of the commits from the upstream original repository still exist and are accessible via any fork. Oh, okay. So it's not just finding a needle in the haystack as to which fork did all of the other commits suddenly go to. You could end up tracking this down from any of the forks if you just happen to find one, or discover it online. So let's try that example, right? Let's go back to our initial starting sort of source root node repository that is public. And hey, if any user were to go and fork it, as I will do up here, again, we can make these changes to our forked org republic for just the John Hammond user. I'll go ahead and create that fork. So now we're back to the side-by-side sort of compare and contrast example, right? On the left, we have the upstream source starting root node repository, the initial public repo, and then on the right, the forked user repo here. Now, what if I, on the source upstream repository on the left-hand side, were to make some other changes after it has been forked? I can say new data, secrets, sensitive code, commit those changes. We can go ahead and add that, make sure that we do have a new commit here, looks like 63FB whatever. And if I were to take note of that commit ID value, which again, we can brute force, we can figure out the short SHA-1 key space. Note that going to this URL, going to that commits on the left-hand side is totally fine, because that is the original repository that it was on. If I try to go access this from the fork, pasting in that commit ID, well, it can see that too. But now if over on the left-hand side for the original repository, if it were to suddenly be gone, if it were deleted, if it were just nuked from orbit and repository removed from the internet, well, then they would still be able to access the commit, even though it is presumably deleted from the left-hand original perspective, but on the right-hand forked perspective from that other user, it's totally still accessible.
If you try to visit one of these dangling commits on GitHub, you get this error message at the top that says this commit isn't actually a part of the history, but then it gives you the data from that commit anyway. GitHub put out this blog saying they do actually garbage collect and delete these commits after some amount of time, but we found dangling commits that were over a decade old.
And looking back at the article, they say, hey, this isn't just some weird edge case scenario. This unfolded last week, and they're writing this article. They say, hey, I submitted a P1 vulnerability to a major tech company showing they had accidentally committed a private key for an employee's GitHub account that had significant access to their entire GitHub organization. They immediately deleted the repository, but since it had previously been forked, they could still access the commit, everything that contained the sensitive data via that fork, despite the fork never syncing with the original upstream repository and that original repository just being deleted. With all that said, I know the sticking point here is, well, you still need to figure out the commit ID, that SHA-1 hash or the very starting short SHA-1 hash. We could brute force it with this small, tiny example, but it might be a little bit more realistic to try to thread this. Hey, make it faster, not as procedural. So I do have this example here that our good AI overlords, friend and foe ChatGPT gave me, where I will just go ahead and tweak and tune this now. This hopes to just take that crappy code and make it a little bit crappier, trying to spam, spray and pray, do some multi-threading to rapidly, hey, try to hammer GitHub and see, can you tell me if these brute force or enumerated SHA-1 hash IDs match a commit value? We could probably just exit. We don't really need to care, again, for our just quick and dirty demonstration. Did want to showcase if it finds a hit, then display it, but bail on out. And the pool of characters, if we want to narrow this down just to be a little bit faster, I think ours started with, it was 63FB0, whatever. So we could probably put those in a fine order to actually determine what should go where. But I think it would be the most fun to show that demo with their last and final example here, accessing private repo data from this article, Truffle Security. They say, look, consider this common workflow for open sourcing a new tool on GitHub. You, as part of your team, I don't know, whatever worker bee organization you're up to, you create a private repository that will eventually be made public. You're going to release this at some point. So to continue your own work on it, or maybe, I don't know, have your own other copy before it goes public, you create a private internal version of that repo via forking, and then you commit whatever additional code for features that you're just not going to make public, or I don't know, whatever use case scenario you imagine up here. And then ultimately, you do make that upstream repository public. So that's given to the world, but you keep your fork private. Now, with everything that we've seen thus far, are you kind of putting the puzzle pieces and seeing how this can come to life? Look, Create a new tool, private, make an internal version of it as a fork, end up publishing and making public the original starting initial repo. So let's try to create that scenario from our org account, just as another secondary account that I want to use here. Let's go ahead and create an initial org private repo. No longer public, but private in this example. And we can keep that. We don't need any description. We can add a README. That's okay. Let's go ahead and build that. Once that's created, we'll end up creating a fork of it from myself, just from John Hammond, because that's, hey, a user in this org, so convenience. You will need to actually change the settings, by the way, if you are using this as an example testbed. Your organization GitHub settings is where you'll have to toggle. In the member privileges section over on the left-hand side, you can actually scroll down to repository forking, and then maybe your team or your organization, whatever allows this, where you have forking of private repositories, totally cool, toggled on. So let me do that here. Let me fork. Now with my account, we'll go ahead and create the fork that we'll call like internal forked from the private org repository. That should be a-okay. We all know that's internal. It is from the project that we will soon make public, but we want our own internal copy. So now that that's done, say we made changes, say we manipulate, say we edit or do whatever as we used to do, in our internal private forked repo, we'll say changes made to internal tooling. We can go ahead and commit those changes. Good by me. And now we'll see the new commit that is added in our internal private forked repository with the commit C23E9, whatever. Now let me copy that SHA-1 commit ID just so we could work with it for the visual demo, and then we'll do it all in code in our brute forcing method in just a sec. But of course, if I were to put these side by side again, our initial upstream private repository on the left-hand side, and then the private forked internal-only rendition on the right-hand side. Now, we just made this commit over on the right-hand side, and if I were to paste that SHA ID, you would see it there as usual. But let's say over on the left-hand side, we try that, and you would, of course, as we've seen just previously, you will be able to still get that contents, even though it is not of that repository, so the fork is accessible. But if I were to make this public, because right now, if I were to open a new private browser, let's say, github.com/the org name JHLLC, repo name initial org private, that is still private, right? So me trying to go to this commit, well, it's going to give me a 404. But once we make it public, back over on the left-hand side for our initial upstream private repository where we did not put the new commit, that is in our internal only fork, if I were to change this repository to public, then we'll be able to go see that in our private window. Toggling back over here where I could grab the commit ID if I'd like. Of course, accessing just the repo on its own, you don't see the update readme commit, but it is accessible even though it's in an entirely different private internal only fork. It's there. So the article continues here. Are your private features and the related code from your internal-only fork viewable by the public once you release it? Yes. Any code committed between the time you created an internal fork of your tool and when you open source the tool, those commits are accessible on the public repository. Any commits made to your private fork after you make the upstream repository public are not viewable, though. That's because you're changing the visibility of a private upstream repository results in two repository networks, one for the private version and one for the public version. Unfortunately, this workflow is one of the most common approaches that users and organizations use developing open source software. As a result, it's possible that confidential data and secrets are inadvertently being exposed on an organization's public GitHub repo. Our question, though, is can we track this down? Just an example, just this one tiny little proof of concept here. Could we find the private commit that's still pulled out into the now public repo or any of these other sort of three different examples that we've discussed? Turns out, using this capability, at least small proof of concept, I'm speed running us to the example once we brute force and find a working short SHA-1 hash, it will get us there. So look, I'm looking at the public repository, what was once private but now made public, and the commit that we know that we're looking for is based off of, I believe the actual full SHA-1 hash is this, right? So C23E, if we were to do our usual ABCDF, I'm actually going to put the C character first just for a faster brute force so we could see it in action. And then I hope, fingers crossed, let's get back to our terminal and see if we'll get a hit. Trying all of these values, and what is it that we're looking for again? C2, so it's got to go through the rest of the alphabet here. The first 4 characters are C23E, so honestly, we could probably make our pool just a little bit easier for us to work in for a faster result. Let's remove all the other letters other than C and E, and then just look through the numbers. I know that's a little bit of like cooking show magic, right? Suspended disbelief, and that we're limiting the pool, but look, just for our understanding, that will get abuse detection mechanism. See, this is why our dumb proof of concept is not ideal, even in the small case where we try to narrow the pool. I'm sure you get the idea now that the brute force will conceptually work, and of course, your mileage may vary knowing the rate condition options, but let's turn this down even further. Letting that cruise through, we should still find a C23E at the end of the day. Hopefully we don't hit the abuse limit and rate limit again. I see 2, 3, I see 2, etc., etc., etc. Did we miss it? Or are we permabanned? Yep. Okay, I did narrow the pool of characters again just a little bit so we could see that it would work through. And I know this stupid crummy example, I think even our multi-threaded thing, it'll try to exit and it won't. Like there, you see it, got a hit, I can Control-C out of it. It's just dumping the full HTML at the moment, but it would include the full commit as we were to display that. We, at the very least, want to know the URL and the short SHA-1 that is actually the one that we got a hit on. So scrolling way up to the top, you can see found. Do have a status code 200 and the URL for what we could publicly access. Here I can open Firefox, right? Totally in another browser here, and you could see that is going to tell us all the secrets that it just left out and about. Now, the rest of the article showcases everything that we have already, noting the SHA-1 commit hash and then how it could be shortened down to the short SHA-1 hashes. Minimum of 4 being the length, that gives us a possible key space brute forcing about 65,536 characters. Obviously, when you bring that up to 5 characters or 6 characters in length, that's going to be much larger. Truffle Security has added this to their Truffle Hog tool, which is open source. It's something pretty cool. You can go use this in a probably better and more sophisticated way than us just spamming the URL on GitHub.
We developed a way to still enumerate and download all of those dangling commits, and we open sourced it with this Truffle Hog command that you can run. The command is slow, and it enumerates the heck out of the GraphQL API, trying every single SHA-1 prefix that's possible. It can take hours.
But they also brought this to the attention of GitHub and their VDP. They say, look, this is the intentional design decision and it's working as expected. They do note that in their documentation and all of it is aware. But I don't think that a lot of GitHub users, and even me, like anyone, really has that thought or that thinking of, oh, when you delete a repository, it is not permanently deleted or actually all removed. The commits, right? That data is still out there. Same thing with the fork, same thing with what you might be messing with. I just think, hey, the awareness or education is probably still worthwhile to get out, despite it is still all known, it's public, and it's totally transparent. It is documented, but it's not a very well known, I don't think, or at least oftentimes thought of, possibility and the implications that come from that. But I'd like to get your hot take, because I know there were a lot of conversations that came from this when this article was out and about on the internet. Do you think this is valuable? Is this worthwhile? Is this an attack surface? Is this realistic? And that, okay, you need to know all the commit IDs, which there could very well be many of them, and if you're trying to brute force them, that might take an eternity, depending on what you got to do. Even the Truffle Hog tool that will work through this ends up saying outright, hey, it's still kind of slow. But it is theoretically possible. So hey, let me know what you think in the comment section below. Please do all those YouTube algorithm things, like, comment, subscribe, and I'll see you in the next video.